Okay, guys. Any of them y'all want to see work? Or y'all still looking at the answers? Okay. Here's a copy of the worksheet and answers. So you won't be left out in the dark. But I posted an announcement, sent out an email, told you where you could find it online. Huh? Thought I did. Well, this is probably remind you that it was due. Yeah, some of y'all need to sign up for that texting application too. That's a lot easier to use than email. Yeah, and so you could text me, and I get text instantly. My phone the email goes to my phone too, but I only have it checked like every 45 minutes or so. Okay, gang, which one y'all want to work? The third one. This is what kind of rectifier is it? Full wave bridge. Full wave bridge. And on the tests, I think do we have tests coming up next week? Next Thursday. I think it's going to ask you to identify what type of circuit we have. Oops. So this is our circuit. It's a full wave bridge. And of course, what's the advantage of full wave bridge? It's got basically one advantage. What's the advantage of full wave bridge? Why even have it if the full wave center tap will do the same? Not because of the diodes, because of what? The transformers. Yeah, center trap transformers cost quite a bit more money than two diodes, or 4 diodes, two additional diodes. So it takes 2 diodes to do a full wave center tap. It takes 4 to do a full wave bridge, but a center tap transformer is not required. It don't mean you can't use one. In fact, we'll use it, but we'll only use 2 of the leads on it. We won't use center tap. So the first thing we need to do is calculate. We can do it 2 ways. Let's go ahead and do the V peak first. So V peak on the primary would be equal to 120 divided by 0.707. You don't have to do it that way. You could do the division first and then do the VP. You'll come up with the same answer. You'll see that. So you got, and that's what I was saying. There's a couple ways we can do it. We could take 120 and divide it by, I can't read. We could take 120 and divide it by 0.707. We could take 120 divided by 12 and get the secondary RMS, and then divide that by 0.707, and you'd come up and get the same answer. So what do we got here? I just like to do it. I like to do it first, and that way you don't have to remember to do it later. Does that make sense? Because this will happen all the time. I see people do that all the time. They'll use the RMS value to calculate the output, especially on like half waves and full waves. We'll go ahead. What we got? 69.73 volts, and this is peak. Then I could take V peak secondary which would be equal to 169.73 divided by the ratio of our transform, which is a 12 to 1. So what does that give us? And you see it gives you exactly the same thing that you get if you go ahead and take 120 divided by the ratio, you come up and get 10, and divide that by 0.707, you get the same thing. So me personally, and this has nothing to do with you, because what I'm doing is looking at the right answers, right? And of course, this is going to be one of those kind of like AC, where, by the way, in this class, you don't get credit for showing your work. But if you show your work, and I can figure out where you went wrong. So if you don't show your work, if I grade the first thing and it's wrong, I'm not going to go back and figure out how you got the rest of those answers. I don't figure that out. But if you show me where you took this one wrong answer and then stuck it in the next thing and you did the math right, then you'll lose maybe one thing and then the rest of them will be okay. Does that make sense? Only if you do what? Show your work. If you don't show your work, I'm not going to figure out, okay, did he take this wrong RMS value, or he didn't convert it to RMS over here, so that's wrong. Well, I'm not going to take the RMS value and stick it through the calculations when you're supposed to be using VP to figure out where you went wrong. But if you show your work, and I can figure out where you went wrong, then you might not. Of course, if you screw up all the formulas and everything, you're still going to miss it. And that happens sometimes too. But like even I of the load, so if you show me how you get DC, even though it's the wrong answer, but then you plug it in Ohm's law right, then you won't miss the I. It'll be circled. So when I grade a test, if you see one of your answers circled, it means it's wrong. But it was right because you showed your work, and I showed you used the right equations. It's just that you used the wrong numbers. Okay, so now we need to calculate what we call VP out. So VP out is going to be equal to 14.14 minus 1.4. Now, why are we using 1.4 here? Yeah, it goes through two diodes, right? So we lose 2 voltage drops. 1.4, is that perfect? No, it's approximation, right? You understand, but it works really, really well. So we get what we got? 12.74. And by the way, normally in this class we can round to 1 decimal point, unless we misprove a law, right? You understand that? So then I can say DC out, or volts DC, would be equal to 2 VP, so 2 times 12.7 divided by 3.14, 2 VP over pi. What have we got? 8.1 or 8.2. I wouldn't take off for 8.2 or 8.1, right? You'll understand it. Because, and of course, this is just regular volts. Up here, this should be labeled VP for VP. Then we need to calculate the rest of the circuit. So I of the load would be equal to 8.1 divided by 3.3K. Or 8.2, it's still going to be what we got. I'm listening. Are we okay? Everybody? Huh?
2.5.
Yeah, milliamps. Now we can calculate the power, and of course, in my classes, you're going to have to calculate power. And why? Why? Well, not only that, but you need to know the work you're actually getting, right? You understand? Power is work. Power is not voltage, even though it requires voltage. Power is not current, even though it requires current. Power is work. So when you pay your bill, your electricity bill every month, it's not a voltage bill and it's not a current bill. It's what? You're paying for the power that you use. You're paying for the work that Alabama provides you, right? You understand? So understanding power is very important. For one thing, like Wesley said, we can choose the right size resistor. Resistors are rated in 2 things. And what's the two things resistors are rated in? Ohms and watts. Watts, and of course diodes are rated in quite a few things, right? You understand? What things are diodes rated in? Or multiple things. What things are diodes rated? What's the main ratings for diodes? Well, every rating is a value. That's a good point. But when you say what's resistors rated in, and you said a value, well, that would be correct because we would say 330 ohms, right? To understand that. So yeah, everything's a value. So what values are they rated in? Yeah, we call it generically we call it PIV. And that's what a lot of books teach. Peak inverse voltage. Most data sheets call this VRRE, repetitive reverse RRE or RRV. RRV, I think. Okay, so PIV. What else is it rated? Yeah, that's the two primary. So IF max. And that's basically the primary things that we're looking for on a diode. Is how much current can we push to that sucker if it's forward biased, and how much can this thing block when it's reverse biased. That's the two primary ratings. Okay, y'all understand that? So if we understand that, then we can go out and just look at those two things on the data sheet. Of course, on how they mount, we got to pay attention to that, right? Some of them solder in, some of them stud mounted, some of them, you got to be cognitive of that and make sure you replace it with the same thing, or try to. Why I say that is I've rebuilt battery chargers and I've got a diodes that met this, even though they didn't mount the same, and I just rigged them in there because that's what I had. But, you know. Okay, so power of the load, PL. We got all kind of formulas right here. You can use V square over R, you can I square R, or you can use V times I. So we'd say 2.5 milli times 8.1, and that would be the power that this load in this situation would have. And when you design a power supply, what do you need to know? You have to design it around a certain load, right? You understand? You have to design it around a certain voltage, and you have to design it around a certain current. Well, as soon as you say voltage and current, you're designing it around power supply. When you buy power supplies for computers, the voltages are standard, so they're specified in watts. So you go out and buy a 450 watt power supply, right? Because all of them provide the same voltages inside a desktop computer, so they're not rated in voltage, they're rated in watts, right? Yeah, because they have several power supplies in there, and it would be kind of hard to figure that out. So we got what here? 40.5 milliwatts? 20, yeah, I think say I can. So what size resistor would I use? We could use little ones. Normally, if we're trying to save money, we'd use like a quarter watt. An eighth of a watt, which is 255 milliamps. A quarter watt, an eighth of a watt actually costs more than a quarter watt. So what does an advantage does an eighth of a watt have over a quarter watt? It's got one. Smaller. So that means it would occupy less real estate. And you know, the ultimate goal, and I can show y'all some resistors, surface mount resistors that would fall into this category. Don't even have leads on. You have to get a magnifying glass out to see the values on there. But this is, we're dealing, especially in digital logic, we're dealing with very, very low powered circuits. So guys, everybody okay? So the first part of the test, you know, it's going to be this. I mean, it's going to be figuring these things out. This is the basics of a power supply. And this guy here would run great. It would run anything that required around 10 volts or so. This guy here would run it fine. Light bulbs, motors. Motors don't care. Electronics would hate this. But it's just, but this is just a step. We got to learn this before we make it constant, right? You understand that? Yeah, the filters and the regulators and all kind of neat stuff that we'll get into. And like I said, by the time we get it here, we'll give y'all some basic rules for good gracious. It's not that hard to build a linear power supply. Just making sure you choose the right size filter for what you want, the right transformer for what you want, how to fuse it, the right regulators for what you want. Building a variable power supply these days are almost, I mean, just basic knowledge, you can build these power supplies. Switching power supplies are another thing. Okay, guys, that was one. Y'all want to see any more of them? Oh, current and primary. Thank you. So we got a 12-to-1, and this is very, very important because normally we got two places we can fuse a circuit. We can fuse it in the load side, which would be the secondary side, so we can put our fuse right here. Or we could fuse it in the primary side, which would be there. Now, of course, the advantage of fusing in the primary side is you're also protecting your transformer. What's nice about fusing in the secondary side is you don't have to do any math to size the fuse. Because well, that's not true. As soon as you know what you need for your load, then you would increase that probably around 125%, and that's what you'd fuse for. Fuses are not in there to protect against shorts. They're in there to protect normally against short circuits, right? You understand? I think NEC specifies we can go up to like 150% on our fuse. But the problem is people just got to understand that if I'm getting 2.5 milliamps on my load, I'm not getting 2.5 milliamps in my secondary. I mean, on my primary. Do y'all understand why? Because it's at a higher voltage. And the transformer is not delivering that current. The transformer is delivering power. Right? You understand? So what we'll do is we'll calculate this power. So that means, okay, 205 milliwatts on the secondary. How many milliwatts are we going to have on the primary? We're going to have 20.5 milliwatts on the primary. That's what the primary's got to deliver, right? Y'all understand that? So I can come over here and, okay, so I is equal to P over V. That makes sense? So I'd say I would be equal to 20.5 milli divided by 120 volts. Fuses are not sized for peak. They're not sized for peak to peak. They're sized for the effective voltage, right? You understand? Because that's what your load sees. Your load does not see peak or peak to peak. It sees the effective voltage. And this would be I of the load right here. I mean, this would be I of the primary right there. So y'all see how we did that? So we took the formula, which is power is equal to V times I, and we just arranged it and solved for I. So whatever power I get in my primary, now the problem is by just taking the current and dividing it by that ratio, is remember power is equal to V times I. Okay, y'all understand that? So what do we come up with the current in our primary? We're going to divide that, not by, yeah. 170.8 microamps. So look, if I was to put a fuse over here, if I was to raise this up to 150% and put that in the primary, that transformer would burn up, right? You'll understand that for the fuse would. And that's the big problem we have, people overfusing. They'll know what's in the secondary side, and then they'll fuse the primary side for that same amount. So this would be a little tiny transformer, wouldn't be rated at, and of course that's another thing is you size your transformer. You want to size your transformer to run the load. So you're not going to go out and buy a 50 amp transformer to run a 20.5 milliwatt load, right? You understand? You'd be spending, you got a transformer here that could charge a golf cart on the secondary side, right? Because if it's, when we say 20 amps, I shouldn't say that. Say a 5 kVA, well that transformer there is a 5 kVA transformer to run that robot, and you see how big that sucker is. So this is the transformers that we have are 12.6 volts, 1 amp. So 12.6 volts, 1 amp, so that'd be 12.6 watts that transformer is designed to handle, right? A lot of your small commercial transformers are rated in volts and amps on the secondary side, because they're designed to go on 120, standard on 120 volts, right? You understand? Most of your commercial transformers, 120 volts on the primary, and then they'll give you the voltage on secondary. And if they give you the secondary current, and they give you the secondary current and the secondary voltage, then you can multiply those two together and get the wattage of the wattage required by the transformer, right? Are we okay? So any more? Sure can. In fact, let's just go ahead and do all of them. Because like I said, on this situation here, there's only 3 circuits. So this guy, so we call this guy a full wave center tap rectifier. So we got 120 volts, 60 hertz. We have a drawing program that we call Electronic Workbench, and it's really, really good. What it does is it simulates programs. This is a full wave center tap. Full wave center tap. Because it uses a center tap transformer. So we have half wave. And then we have full wave center tap, and then we have full wave bridge. Okay. The one we went over first was a full wave bridge. This is a full wave center tap, so it identifies that this requires a center tap transformer. So let's do it the other way. Let's do it the other way this time. So let's do the ratio first. So I'm going to say VN, so V primary is going to be equal, we know V primary because it's given. So let me put that. So V secondary would be equal to 120 volts divided by 10. Where did the 10 come from? That's the ratio of the transformer, right? So we'd come up and get 20 volts. And we can go ahead and convert it to V peak. V peak secondary would be equal to 12 volts divided by 0.707. What are we at? 17. We got one that we need to go to 1 decimal point. Is it? Okay, then that's what we need to put. So we're rounding to 1 decimal point. So we're not rounding to whole numbers. So what we'll do in this class is round to 1. So 16.7 volts peak. No, 16.9. 16.97. So you're right. Yeah, that's what. So 17. Yeah, it'll round 17. So 17 volts. Okay. Then I'm going to take V peak secondary. We can still call it that. I'm going to take the 17 volts and I'm going to divide that by 2. Now you realize you could have done that here, because what we did, the 17 volts is right there. Y'all understand that? But that's not what's across the diodes. The diodes don't, the diodes in a full wave center tap never sees the full secondary voltage. It just sees what? Sees 1/2 of it, right? You understand that? So what we got? If you want to go ahead and do it at that step right there, that's fine. You know, a lot of people just stick it out there. They'll come up this and right off the bat they call that V peak secondary. Oh yeah, it's fine to do it the other way too. And I said that we're just going to work this another way. Yeah, you could go ahead and convert this to VP first, right? And then you could come over here and you could do that whole thing in a whole thing. You know, you could say divided by 0.707 divided by 2. You could do that in one whack too, which to me would be better because that way you won't forget to divide it by 2. The biggest problem we have with people on this thing is forgetting to divide the secondary voltage by 2. The next problem we have is to take the 120 volts, divide it by 10, and then use 120 volts the rest of the way. And forget to divide by 0.707. So they don't take RMS and convert it over to VP. So the biggest problem we have with power supplies is, number one, people not converting to VP. They use the RMS value to calculate. And on this guy, what do? They forget. They forget that divide by 2. And I don't know what to say, guys. You know, that's a pretty important thing to do because you're going to end up with twice the load. You're going to end up with twice the voltage, right? You understand that? You'll be off by a factor of 2 all the way down the line. What we call VP out is going to be equal to 8.5 minus 0.7. Now, why are we using points? Even though there's 2 diodes, only one of them is being used at a time. Only one side at a time. On the bridge, we're only doing one side at a time too, caddy corner side, but it always flows through 2 diodes. So what we got? What's that? 7.8 volts, and this is then our DC, volts DC would be equal to 2 times 7.8. 2 times bridge, 7.8 divided by 3.14. Five volts. Then I of the load would be equal to 5 divided by 2.2K. That's the same size as the other one. What's that?
Roughly 2.3 milliamps.
2.3 milliamps. Power for the load would be equal to 5 volts times 2.3 milli. Have y'all tried the other one, V square over R, and it comes up and gives you the same thing. So what we got? What's that?
11.5 milliwatts.
I of the secondary and I of the primary would be equal to 11.5 milli divided by 120. And you don't. What's nice about that? You don't have to worry about the divide by 2. Power delivered by the load is the power delivered by the transformer. So they don't care how the thing's hooked up, right? You understand? If you had multiple winding transformers on the secondary, you would add all the powers together. And that would be what, then you just add them together, right? Because one of the main formulas for PT is what? P1 plus what? P2 plus dot, dot, dot. Is that for series? Is that for parallel? Or is that for series parallel? It's all. Total power is total power. So you can literally go to your house and look at all your devices. You know, and if you're looking at a TV, it's series parallel, right? It's got a bunch of, and you can look at the power rating and you could add that up to your power bill. You know, your power is a parallel circuit. So everything you have plugged in, you just add the watts together. You just add them together. So total power, one formula is it don't care what circuit it is because that's what power, that's the work it's trying to do. It don't care if it's parallel. It don't care if it's series. The power source has got to do all that work, right? So yeah, we could do that. So if I got a multi-winding transformer, we could go, some of them's full wave, some's half wave, just like the trainer. We just add all the powers up, and then that's what the primary's got to deliver, right? Normally when we do that though, we do the rating of the transformer, right? You understand? We calculate the power rating of the transformer, not necessarily the power rating of the load. Okay, so what we got here? What else would you think we would use? That's the load. I mean, tell me what's on your mind. Why that's the work. What? So this power supply is designed to run that resistive load. That's its purpose in life. So when we talk about power, we're talking about power delivered to the what? To the load, right? So when we calculate the power of the circuit, we don't care about anything else. Now, of course, I'm going to have to make sure I choose a transformer that has the ability to provide that power, right? That's it. I, what's the formula for I? Huh? Yeah, power is equal to V over R. So here's my voltage on the output. That's what my load sees. Now it's pulsating, but my load does not see the pulses. My load averages that out. So if I had a 5-volt motor and I put it on that sucker, this thing would run. I mean, it'd be happy. Yeah, but this is AC. This is still AC. That's still AC. The load don't see that. The load sees what comes out of those diodes. It don't see the 120 volts on. That'd be like me using 120 volts to calculate the load, the power of the load, right? You understand? So what do we see? We don't use this. This is V peak. This is V. What does the P stand right there for? Yeah, this is V peak out. And anytime we use the term peak or peak to peak, we're talking about AC. Over here, this is not V peak out. I said volts what? DC. Now, I don't know. I think the thing says DC average because that's exactly what it is, but it's still volts DC. So if I took my dang voltmeter and put it across this load, it would measure about 5 volts. Of course, it's not going to measure exactly 5 volts. For one thing, we don't have this transformer here. We could do it on electronic workbench. Of course, electronic workbench, when I say 120 volts on electronic workbench, it is exactly 120 volts. So odds are if we did this calculation and we looked at it on electronic workbench, it would be perfect. It's a neat little program. And that's one of the reasons why we don't upgrade these computers. We have a couple applications that won't run on Windows 7. And one of them's electronic workbench. But it's a simulation circuit. Huh? Yeah, it is, but electronic workbench, it's not called, it's called, what's it called? It's changed names. And probably for a 20-seat license on that would probably be well over, probably around $10,000. So we've got this version that does what we needed to do. Y'all got it on y'all's, y'all got it on y'all's computer there. That computer right there is turned on. By the way, there's nothing wrong with that computer there. It's got that little note do not use because that's the one I remoted to for these classes. It looks like it might not be turned on, but it's a really neat simulation program. We had an instructor try to use it to teach DC, and what you do is you draw your schematic and then you put meters into a schematic. The students would get into these classes that have no idea how to wire a circuit. How the circuit is wired, and you have to understand the wiring of the circuit. What's their ultimate goal when they develop a circuit board? Cheap as possible, and one of the main factors of circuit boards is their physical size. So they're going to put those things. They're going to arrange them. They're going to put them over here, over there, and their ultimate goal is to do what? Small as possible. The new simulation program though actually will do a printed circuit mask for you. And if you put the value of all these components in there, it'll calculate the billing and order for you and all kinds of stuff. So if you were designing solid state circuits, $10,000 wouldn't be, but just the amount of effort it would save them. It'll try to do a single-sided board for you. It'll do the math for them. It's really, really neat. Generate a parts list for you. If you enter the prices, it'll develop the cost. If you enter retailers, it'll order for you. Okay, guys, y'all okay here? So wait, what did we get here for the primary current? So that's what people don't understand. They don't understand how we can get 2.3 milliamps on the secondary with 95 microamps on the primary. Y'all understand why? So we say a transformer steps voltage up and steps voltage down, but it's also changing the current. So if it steps the voltage down, current's got to go up. Right? You understand why? To deliver that power. So, and this gets people confused because they're thinking about Ohm's law. So Ohm's law always says if V goes up, if voltage goes up, current goes up. But we're not talking about the load. We're talking about the source, right? And it's guaranteed if you raise the voltage on the load, the current in the load's going to go up. If you lower the current on the load, the voltage on the load, the current's going to go down. But we're not talking about the load. We're talking about what's going on in the source, right? You understand that? So yeah, if somebody put 240 volts in here, it'd blow your resistor up because now the output of the secondary is going to be higher. The output of the current is going to be higher. The voltage to the load is going to go up. If the voltage to the load goes up, then the current goes up. That's what gets people confused, especially in DC. So let's go ahead and do the half wave. Oops. The icon for email and that. Oh, okay. Let me, and that should have been on both of them, and that's very important. That's important too. So let me just bring up the, I've already deleted it, and I'd have to cut and paste it. No, this would be a positive supply. Why would that be a positive supply? Yeah, well, the anodes are pointing toward the source. So what we do real fast, we could trace current all over this thing, but all we need to do is just see what's pointing toward the source, right? So even on the full wave, I can come up here. All I'm concerned with is this guy right here, because that's connected to what the hot lead or and the anodes are pointing toward the source. So what's his power supply? It's a positive supply. You understand that? So I'm not even looking at these over here. Here's my load. Here's common. Common is the guy that doesn't have a polarity, right? You understand? Because common is what we make our measurements to. So if I take my meter and go from common to common, what would it measure? Your voltmeter. It's going to measure 0 volts because that's your common, right? You understand? So in electronics, normally what we do is we establish a common. And that's what we usually measure our voltages relative to. In DC, what we normally do is we let you probe all inside a circuit. Normally, especially in power circuits, we don't do that. We measure relative to a common. And what we like to do is take our black lead and put an alligator clip on and clip it to our common, and then probe with one hand. And what's the advantage of probing with one hand? Yeah, so there's no way in the world. This is probably one of the most dangerous paths. This is one of the most. We have 3 dangerous paths. Left arm to right leg. Right arm to left leg. Left arm to right leg, and then hand to hand. That's the 3 most dangerous paths for current to go through. And both of them are bad. DC has a tendency to do what? Not let you go. AC, if it goes to your heart and it overrides, it's going to try to make your heart beat at the frequency of the AC. And it can't, right? You understand that? So both of them are dangerous. The AC probably a little more because, especially across your heart, because it didn't take much to override the impulses from your brain. Okay, so we're looking at, and of course this one right here, this half wave is going to be what? I can't reach, I need to move my table that way. I can't reach, yeah, this is going to be a negative supply. Now, positive supplies are by far the most popular, but, you know, if you get into electronics, especially video or you know, sound systems, you're going to have AC. Because we don't put DC on speakers. We have to put AC on speakers. Or you'll burn them up. So the new iPhone 7's got 2 speakers on it now, just stereo. They added 2 cameras. One of them's a telephoto lens on the iPhone 7. So it's actually got a telephoto lens on there. Instead of, because what happens when you start blowing up, y'all ever done that? It starts getting really grainy, it starts pixelating with the camera. So they put a telephoto lens on the iPhone 7. And they did away with what? They did away with the headphone jack. For y'all people that want the newest iPhone that's out there. Oh yeah, and it is water resistant. My son said to 1 meter. Which is only about 3.3 feet. So you could probably go swimming in it, but you couldn't dive. And you could take a shower in it. If you dropped it in the commode, you'd be fine. Well, it's better. It's better than nothing, right? I mean, it's a lot better than nothing. 3.3. What's that? No, you lose it. So what do we want to do here? Let's go the other way. Let's do VP first. So I'm going to say VP primary will be equal to 120 volts divided by 0.707. What do we get? 169 point what? 169.7. Then I would say VP secondary would be equal to 169.7 divided by 5. Everybody know where the 5 came from. That's the ratio of the transformer, right? Did you do your worksheet with? What we got? 30 what? 33.9 volts peak. Then we'll calculate V peak out, which is what feeds our rectifiers. This is going to be 33.9 minus 0.7. What's that? 33.2 volts. And then volts DC is going to be equal to 33.2 divided by pi. Why don't we multiply by 2? Huh? Only using one alternation. What do we get?
10.6.
So I, my load would be equal to 10.6 divided by 1K, and I can do that in my head. That's 10.6 milliamps. I like 1K. It's 1 milliamp per volt.
On the sheet that this is, are we supposed to do that?
We're not through. You could. I think what we're looking for is not a negative. Really, there's no such thing as a negative current. What we have is we have a negative voltage that causes the current to flow in the opposite direction. So resistors have a polarity, and resistors have a polarity when you set up the way the current flow through them. But the only way we get a negative is with voltage, so no, you don't need that on current.
So we
Or
don't,
power either.
we don't need to do that on the test list of voltage.
We need to have the vote, huh?
We don't need to do that on the test list of voltage.
The list of voltages like negative. Is that
We do
what
need,
we need to list the voltages negative.
okay.
I mean, because there's a lot of difference between a negative. I thought you said current. That's what I
I'm
heard.
sorry.
That's what got me confused. Yes, that needs to be listed. Yeah, you said current. Yeah, voltages are voltage is what has the polarity, right? You understand? And what does the polarity determine?
Direction.
The direction of the current. But the current itself has no sign, right? But, huh?
On the sheet it does.
10.6 milliamps has a minus beside it.
That's
Okay, then that's,
10.59. I don't know why.
yeah, that shouldn't have, that shouldn't have. I'll take that off. In digital, you'll run into the negative current designator. But what they're trying to do is they're trying to get us to determine which direction the current is flowing in or out of the IC, which is interesting. You know, take digital, you don't like that. Because a digital circuit outputs AC, but it never changes polarity. Figure that one out. So when I first got into data sheets for digital, it confused the heck out of me when they said the AC parameters, and then I'd say AC digital work off AC, it's DC. Then when you start understanding the concept of what we call syncing and sourcing. So when it's sourcing, the current flow is in the gate. When it's syncing, current flow is out of the gate. So so if it provides the power and something else provides the ground, then the current flows into the gate. When the IC provides the ground and something else provides the power source, then the current flow is out of the gate. That's one of those when the light comes on. And I complained about digital data sheets for a long time. But I knew those people at Texas Instrument had to be smarter than me. But yeah, we don't need the current there. This is where you have to make sure you put the polarity right there. Everybody okay? Because if I came over here and said power is equal to minus 10.6 times, then I got problems, right? You understand? Because now I'm going to come up with negative power. Of course, if I said a minus 10.6 times a minus 10.6 milliamps, then we'd be okay. So we don't use, on our power formulas, we don't use polarities on our power formulas because power is power, right? And if we came up with negative power, that means Alabama Power would be paying us. Power is equal to V. What D am I going to use? 10.6. And then what current am I going to use? 10.6 milli. And also in watts and ohms law, we don't put the units in there because well, they don't cancel. That's the problem. They don't cancel each other out. They don't cancel each other. V and I do not cancel each other out, right? You understand that? So if I didn't, mathematically, we would say power is equal to something IVs, right? You understand? Because they don't cancel each other out. But what we're doing is we're dealing with ratios where we say, okay, I is equal to the amount of voltage divided by what? The amount of resistance. It don't say if you didn't leave off those units, then if you did that in algebra, you'd fail the class because V and R do not cancel each other out. Right? You understand that?
It's almost like physics of meters.
It is meters per second where they're saying, okay, this ratio I is equal to the amount of voltage divided by the amount of opposition. And then that's always true. So that's one thing where your equations don't work like you learned in algebra. So that's why I tell y'all don't put the units inside power formulas, current formulas, Ohm's law. We don't put the units in there. So I don't put 10 volts divided by 1,500 ohms, right? You understand? Because mathematically they wouldn't do what? They wouldn't cancel out. So what we got here? But if y'all put them there and you put the right units, I wouldn't mark off. It's just that you'll never see me do that. See, so when I do that, no units, right? So all we got? 112.2. No, 112 milliwatts. So I, the primary, would be equal to 112 milli divided by 120 volts. Now, of course, you got to put your engineering notation up there, right? You can't drop that because that's part of the weight of the number. We get people in DC, they'll drop units. So that's what we got. What's that? So your transformer has to deliver. So what's the function of the transformer? Well, it's got two functions. It delivers the voltage. It sets the voltage that you need on your load, and also it's got to provide the power the load needs, right? We say that a transformer steps voltage up and steps voltage down, but it's also the current's going in the opposite direction. So that's why when you look at a transformer, you can tell the low voltage side from the high voltage side just by looking at the size. If you can see the windings, your low voltage side is going to have the bigger gauge wire, and your primary is going to have a little old tiny wire. Your high voltage side is going to have a real small one. So over here on the ABB robot, we have a step-up transformer because we don't have 440 available here in this building. I don't even know if we got 440 available on campus. I don't think we do. So the primary we have here is we run what they call a Y, a grounded Y. So we have 208 three-phase, we have 208 single phase, and we have 120 volts single phase. And that's the only voltages I know of that's available here. So if we need lower voltages, we use a transformer. If we need higher voltages, we have to use a transformer. I think it's a 5 kVA transformer. So your big transformers are going to be rated in use the kilowatts. Your small commercial transformers are probably going to be rated in volts and amps. On the secondary, they give you the voltage in amps on the secondary. It's up to you to do what? To figure the amps required by the primary. So what do we do to figure out the amps on the primary? We would take the output amperage of the transformer, would multiply it by the output voltage of the transformer. Then we would divide that by the turns. Then we'd take that power, right? You understand? Did I say divide? We would take the output current of the transformer, multiply it by the output voltage of the transformer. And then we would divide that by the voltage on the primary, and that would give us the primary current. So I've never seen a transformer where they rate the primary current. They rate the secondary. Now commercial, industrial transformers, the transformers are usually rated high side and low side, right? I told you that. H is for highs, and L and X is for what? Lows. Okay, guys. Any questions? So there's a second worksheet that we usually don't give out in in class. What we do is we put that up on Blackboard, and what we do is we put the worksheet up there, and then we put the answer sheet. So what does that give you the ability to do? It gives you the ability to look at other circuits, right, besides these. And of course, the only thing that can really change is your input voltage. Watch your input voltage. Don't take for granted that it's going to always be 120 volts. So like we're saying on our robot over here, it's using 210 on the input, and then it's not it wouldn't be 440. It'd only be 440 if we put 240 on the inputs. Are we okay? Any questions? And of course, this is all the deal. We're trying to figure out what the power supply could do, and understanding the math and understand where this thing comes from. You know, and like I said, if you're going to design your own power supply, then you would have to, especially a variable one. We'll even show you how to do that. There's a real popular 3-terminal regulator called an LM317, which is a variable regulator. And we'll show y'all how to actually take the output of that as a reference and then run it through a sure enough transistor to get. I'll bring my power supply in and show me the way. I made mine out of a golf cart charger. Somebody gave me a golf cart charger. And it's in the same case. It's the original case, except it's got meters on it. So any questions here? Okay, guys, we need to go and do our lab. Somebody's going to have to take this table right here, move it over here by the ABB robot. I don't know who was working on it, but this is not where it goes. They moved everything around. They unplugged everything. So I've been trying to get it put back together. They waxed our folders. The chancellor of the 2-year college system came and visited the campus today to look at our mechatronics program that we're fixing to start offering. He was impressed. All right, let's go lab. Wait a second. Let's go over those capacitors a little bit. Yeah, because we went over that in the lab, and some of y'all hadn't had AC. Have you had AC, Brandon? We don't get into capacitors. Capacitors are really, really neat. We use them primarily to. And here we're going to use them as our primary filters. Capacitors are in